So in this video we're going to start a series of videos looking at the circle theorems, beginning with the isosceles triangle theorem, which says that the base angles of an isosceles triangle must be equal. Okay, let's start by making a mark here, and we'll draw a line of a fixed length here. Okay, and if we draw a line of the same length going in a different direction, then when we join this up, obviously we're going to get an isosceles triangle. Why? Because these two sides, this one and this one, we've drawn equally, so they're equal length. Now, in relation to circles, what we might want to think about is the circle for which this is the radius. So if we draw now a circle, so reach for our compasses, put our compass in the center, draw around, then we're going to get something like this. And now we can remove these indicators here, because one of the things that we might be tested on in a test paper or an exam is that we know that the radius of a circle is always going to be the same length. So this length and this length must be equal. We don't need to be told that they're equal because we've got this circle now. So here we've got two equal lengths. Okay, next thing we're going to do is join this up to make an isosceles triangle. And now let's put some values on our triangle. So let's say we have the radius is given as 3, so we're just showing this on one length here, and let's say that this angle here is 30 degrees. So 30 degrees is that angle there. Okay, now I'm going to use a different coloured pen just to show how we can begin to fill in something like this. So obviously we can now say that this length here, if this was x, we would say x is 3. But it's such an obvious thing, or it should be an obvious thing, that the radii are equal, that it's unlikely that you're actually going to be given that as the main part of the problem. So let's say that you're given that x is actually this angle here, and we're asked to find that. So that's problem A. Okay, let's call it problem A. So how do you find x? Well, what have you got? You've got this side length here, 3, and you've got this angle, 30 degrees. You don't know what this angle is yet. You can fill in immediately that this must be 3 as well, so that's the first step. So what we need to do is find this angle here, and then we should be able to find the third angle in the triangle, which is the missing angle x. Okay, so let's start by filling in this angle here, and probably the neatest way to do that is to call it y. So we'll call that y. So to find y, we're going to use our isosceles triangle theorem, that the base angles of an isosceles triangle must be equal, and it's an isosceles triangle because the two sides here are equal, therefore these angles will be equal. So how do we write that down? We'll write y equals 30 degrees, and then we need to give a reason. So we can write base angles of an isosceles triangle. So I haven't got much room, so I'm going to just write isosceles just for clarity. But you might also, and you should get the marks, you might also want to do a little diagram with these sides shown as equal. So base angles of an isosceles triangle. And I would suggest writing out the word isosceles, just to be clear. Okay, so that's the first step, if you like, of finding the missing angle x. And what we've done is given the angle here, the value, and then we've given the reason that we're able to conclude that that must be 30 degrees. Okay. Next thing then, we can go straight to finding x. Now x must be, if it's the third angle in a triangle, any triangle, the angles sum to 180 degrees. Now there'll be a separate video on this, or you can look it up yourself, and it's common knowledge, I think, that the angles of a triangle add up to 180 degrees. Nevertheless, we should give the reason, so x must be 180 degrees minus y minus 30. Or you could have said 180 minus 2 times 30, which might have been slightly better. Let's do it that way. Okay. Minus 2 times 30. And we don't need to put that in brackets because of the order of operations, but just to make it clear, let's do that so we know that we do that first. Okay. 180 minus 2 times 30 degrees, which is going to be, the reason is, so if we put the reason again in brackets, sum of angles in a triangle. In any triangle, notice, not just an isosceles triangle. So in any triangle, the angles will all add up to 180 degrees. So we've now got x is 180 degrees minus 60. Which is equal to 120. So x is 120 degrees, and we've solved our problem. Now, always do a quick check. So how are we going to check? Well, simply by adding up the angles that we've now derived. So we've got 30 here. Little that arrow. We've got 30 here. We've got 120 here. So our check is simply that 30 plus 30 plus 120 does indeed equal 30 plus 30, 60, plus 120, 180 degrees. Therefore this must be. Okay, so let's now draw another circle to have a look at a very similar problem. So if I mark the center of my circle here and then draw a perimeter like that, draw the circumference I should say, what I'm going to do now is draw a tangent. So a tangent is when the straight line touches just one point of the circle. In other words, it doesn't go in which case it would cross 2 points, but it is touching, so it's just touching at this single point here. So now if I draw another one, again bring it right down so it just touches the circle. Then what I can do is join up this point where it touches and this point where it touches, okay, and down here. And I should know that when you've got a tangent and a radius, the angle here is always at 90 degrees. So this angle here and the other side of this line will be 90 degrees. So just putting those in to make that clear. The other thing that's interesting and useful to know is that these two lines, from this point to where it touches the circle, so the length of this line here must be equal. So this side must be equal to this side here. And if I draw a line down like this, then you can see again that I've got not just the isosceles triangle here, but also an isosceles triangle here, because these two are of equal length. Now, why are they of equal length? We'll explore that in part 2 of the video, but just for the moment, if you've got a tangent, if you've got two tangents, when they cross, they create two equal lengths. So it's another case in which you know you've definitely got an isosceles triangle. So again, this is something that might be tested, and so you're not necessarily given this. Okay, you've got to be able to spot that this is an isosceles triangle. So let's add some values again. Let's say that this is, let's say, 65 degrees in here. Again, let's call this x. So x is this angle enclosed by the two tangents. And let's put a length on here. So let's say we know that one of these lengths from here to here is going to be 5. Okay, so one of the lengths of the triangle is 5. Can we find x? So you might want to pause the video and give this a go, or just watch the worked solution. So let's now work out the answer step by step. So problem B, let's write it out here. So problem B is going to start with the idea of the isosceles triangle. So we've spotted that it's an isosceles triangle, therefore we can fill in the missing side. We know that this is also 5, and this is therefore an isosceles triangle. Therefore we know that this is going to be equal to this angle here, because even though it's on its side, these are the base angles, okay, because this time it's sort of pointing in this direction. So we've got 5, 5, we must have 65 here. But to give ourselves a step by step, let's label this again y. Okay, and close it carefully and write y equals 65 base angles of an isosceles triangle. And we would write out isosceles just to be clear, but I'm just going to write, do a symbol like this. So base angles of an isosceles triangle. So we've got the y equals 65. Let's move down here to complete the problem. Now what we've got to do is find x. So x must equal 180 degrees minus 2 times 65, so 2 times 65 degrees, which is equal to 180 minus, well, 65 add 65 is going to be 130, so it's 180 minus 130, so x must equal 50 degrees. And we need to remember here, sum of angles in any triangle. Okay, that looks like 56. Let's just make it clear that's 50. So x equals 50, and we're going to finally just check our answer. Again, simply adding up the angles, so now we know that this is definitely 65. We can now add up, so let's write check 65 plus 65, and here we've calculated that this must be 50, so plus 50 gives us 130 plus 50 equals 180. So we know that this must be. Now, what if we have to prove the theorems that we've been working on in this video? So let's just draw our circle again and draw our triangle using the two radii. And what we're going to do here is we're going to use this to prove the theorem that the base angles of an isosceles triangle are congruent if we have an isosceles triangle. So if these two sides, in other words, are the same, they're equal or congruent, then the angles here will also be congruent. We've been assuming that, but now let's prove it. Okay, the first thing we need to do is bisect this angle here, which we can do by using compasses. So if we now make a couple of arcs down here and here, and then move to the other point here, and again, okay, make a couple of arcs. Then if we join these two intersections together, it should go through this point here, and it will bisect this angle. So that's the classical method of bisecting any angle. In other words, turning it into two angles. So what we can do now is turn this into two triangles, and this is a common method for proving these kind of theorems. So what we've got now is we've got two triangles. Now we've got in fact right angled triangles, but we haven't proved that yet. So we have to go systematically through that proof. And in fact it's not the right angled triangles, the right angles at the bottom that we're looking for. We're trying to remember, we're trying to prove that these two angles here must be equal because these two triangles are congruent, they're the same. In other words, they reflect one another, but the angles and the side lengths are the same. Okay, so what have we done so far? We've got two angles. So we've got an angle here, which, because we've bisected it, must be equal to this angle here. So those two angles are congruent, they're the same. We've also got a side, this side here and this side here. They're both radii of the circle, so those must be the same as well. So we've got a side and an angle must be the same as a side and an angle. Now to make this clear in our proof, what we can do is label the point. So we'll call this 0 or O. This can be A and this B. And we can't really assume this is a midpoint yet. We certainly haven't proved it, but I'm going to label this M. Okay, now if you've got to prove that two triangles are congruent, you want three properties. And so you want to say one side and two angles, for example, must be the same. Then you've got side angle angle congruence. Or you want to say two sides and an angle, the angle in between, are congruent. That's another proof of triangle congruence. So we're going to use that last one. We're going to say we've got side, angle, side. And why is that? Because we've got a common side. So we can say OM, okay, is common. Yeah. OM is common, so that gives us these two sides must be the same because they're common. We've got AO must equal, oops, OB. Let's just raise that, okay. Equals OB. Why? Because they're radii, so we can just write radii. So AO equals OB, that gives us our two sides, and we can say angle AOM must also equal angle MOB. Is that right? Yeah, angle MOB. OB. Why? Because they're bisected. Bisected angles, so that angle bisected, which means cut exactly in half. Let's just make that a bit clearer. So, there we go. Therefore, we can say we've got side angle side congruence, and we usually just notate that SAS, and all it means is that the angle is between the two sides, and SAS congruence means we have congruent triangles. So in other words, everything must be the same, all the sides must be the same, all the angles must be the same, and therefore the base angles, which was what we were going for here, must be equal. So we say, therefore, angle OAM must equal, angle MBO, or OBM, let's do OBM, must equal angle OBM, which was to be shown. So if we were asked to show or to prove that the base angles of an isosceles triangle must be equal, then these are the steps that we use to prove that theorem must be correct. Okay, so now let's look at the other triangle that we were looking at, and in fact it was this idea of the sides made from these tangents being equal. So we had the theorem that when you've got two tangents from here to here, they must be equal lengths. So from here to here. So if we remove this now, what I want you to look at is in fact two larger triangles that we're going to prove are congruent. So if we draw the white lines over these. Now, what have we got here? Well, by the other theorem, which is more basic, that we've got radii and tangents. A radius will always be 90 degrees, will always form a right angle with a tangent, because that's the definition of a radiant-tangent relationship. So you've always got 90 degrees here. So we can draw that in straight away. Let's get the ink colour. There we go. So if we draw that in, we know that these are right angles here. Then, okay. Again, basic classical principle proposition. So if we once again label this, so 0, let's have B C down here, why not, and D here this time. Okay, so we've got O, B, C, D. So we've got triangle OBC and triangle ODC. And we've got to prove that they're congruent, because then that will prove what we want to prove, which is this side is equal to this side. Okay, well, how do we do that? Well, it might be tempting here to, well, let's start with this common side. So we can say that OC is common, OC and, no, sorry, OC is common. There we go. And we could say, well, we've got an angle here, in which case we'd have these sides. So we've got OB is the radius. So let's mark these with 3 marks. It's equal to OD. So in other words, what have we got? We've got side, side, And then we've got this angle, because we can go clockwise or anti-clockwise to get the order right here. So side, side, angle, or side, side, angle. So we're going anti-clockwise that way. So we might be tempted to write side, side, angle. Now this is a common pitfall, so be careful of this one. Side, side, angle congruence, and you can work this out separately. You'll see, if you just work it out on paper, that when you've got two sides like this and the angle that's not in between, you do not have proof of congruence. And a little tip here is, if you read it backwards, ASS, which you can do, you've got ass. And people say that you're an ass if you think that SSA gives you congruence. So we can't have SSA, and that's the exception to this kind of rule, that you need these three properties. So we need to remember that one, and we need to look for an alternative proof. Well, we've got one. Because if you have a right-angled triangle, which is what you have here, then this side must be the hypotenuse. So you've got hypotenuse congruence, and you've got these two sides. We definitely know they're congruent, so you've got side congruence. So if we remove the one that we're not allowed, SSA, what we can say is we've got right-angle hypotenuse side congruence, or RHS congruence. So if you have the hypotenuse and any one of the sides, we call this RHS congruence. We can write it like this. RHS congruence. It's very common to have RHS congruence. You often do get these right-angled triangles. If you've got RHS congruence, then you've proved that all the sides and all the angles of both these triangles must be the same. Therefore, CB must be the same, must be congruent to or equal to CD, which was the theorem that we were trying to prove or to be shown.